Hi, in this video we are going to see NP hard traveling salesman problem. So what is a traveling salesman problem? If a graph is given with set of vertices V and set of edges E, the objective is to find an optimal solution to traverse through all the cities with the least cost. Right? So here you have to take two constraints. One is the distance between every pair of cities is given by D of I, J, and it is not necessary to be the same if you are taking the distance from D of A, I, J and D of G, I. That means when from distance from A to B is not necessary to be the same as B to A, and also it is not necessary to obey the triangle inequality. For example, in this graph, if you are taking the distance from A to C, if the direct distance from A to C is not necessary to be equivalent to the distance from AB plus BC, right? So with these two constraints, we have to find the solutions. So for example, if you are starting from the city A and we have to traverse through cities B, C, D in any order, and we have to come back to A. So what are the possible solutions for this? You may have 6 possible permutations here. So that means you will be having n minus 1 permutations. Why not n permutation is the first city we have already decided. So as once we have decided this, the remaining 3 cities are getting permutated. So we are getting n minus 1 permutation. So totally 6 possible solutions are there. But when you are increasing this n, it will not, the time taken to solve this, finding this optimal solution will not be in polynomial time, and it will be worse than that. In the case of 20 city problems, it is taking 19 factorial permutations, and in the case of 100 cities, it will be taking 99 city factorials, right? So it is very tough to find optimal solution for this, and so that's why this traveling salesman problem is NP hard problem. Let's see whether the decision traveling salesman problem is NP complete or not. So what is decision traveling salesman problem? Instead of finding optimization for the problem, here we are just going to check whether that path is existing or not, right? So it is similar to Hamiltonian cycle. So let us try how to reduce this TSP using Hamiltonian cycle. So first let's create an instance of TSP. A TSP instance is given by a set of cities. Each city is represented by C1. And the distance between the cities are given by this D of Ci, Cj. That will be equivalent to, we are going to include for each of the edges. So it is assigned as 1 if the edge is available. So for in this example graph, we are having 4 vertices of 4 cities, and there is for each and every direct edge, we are going to assign the cost as 1. Right? So in case if you don't have the city, we have to assign. So that's why first we have to find the complement for this graph. The complement for this graph will have only the edges which is not present in this graph. So the only the edge which is not present here is Vx, right? So for this Vx, we are going to assign the cost as 2. For all the remaining edges, the cost is assigned as 1. Now we have to find randomly choose the path, right? So if I choose the path as U, V, X, W like that, so we are going to take the sum of all these edges, and if it is equivalent to n, at most it will be equivalent to n, as we are giving the cost of each of the edges as 1. So if it is at most n, we can say this one is optimal solution. If it is greater than n, then that path is not existing, as it is using some of the edges which is having value greater than 1. So then we can say that is not an optimal solution. So as this algorithm can be easily verified by using one algorithm in polynomial time, we can say this decision TSP is NP complete, but optimal TSP is only NP hard and it cannot be complete. Thank you.